Yeah, everyone's doing like two, so depending on what you
Yeah, that's like, I felt like they were only doing fine math.
Yeah.
Okay.
Yeah.
Yeah,
So we have a couple,
Yeah.
I have to.
I mean, that's the only thing that was most looking at one of the last. I wanted to do ECE, but I was like, yeah, money that's the I think not, or I think like, I'm sure we might be on the.
You were saying is the.
I think I can just handhold this, right? Yeah. Cool. Okay, hopefully everyone can hear and see me. My name is Vishwat Sudhakar. I'm a PhD student in the CPS Hall Lab. And it's my honor on behalf of our advisor, Dr. Payich, to introduce our speaker today for the Athena series. Dr. Spencer Hallyburton is recently defended his PhD in electrical and computer engineering at Duke University and the Cyber Physical Systems Lab, where he conducted research in assured autonomy under support from the NSF Graduate Research Fellowship. His security analysis of perception algorithms led to the discovery of the Frustum attack, a critical vulnerability in multi-sensor fusion. In response, his work now centers on trust-based and neurosymbolic approaches to security-aware sensor fusion. He combines estimation theory, deep learning, and Bayesian statistical methods to develop resilient autonomy. His research has been presented at leading conferences spanning security, cyber physical systems, and control. He is also the primary author of AV Stack, an open source platform for modular and full stack AV design. Without further ado, I'll pass it off to Spencer.
Awesome. Thanks for the introduction, Vishruth. Yeah, so I just recently finished my PhD in the Cyber Physical Systems Lab. It's been a wild ride. I think I've been here for almost the entirety of the Athena program. So it's really been cool to see the impact that has had on the research that we've been able to conduct at Duke University and then all of our collaborating universities. So today I'm going to be giving a window into one of the research projects that I've been spearheading throughout the last couple of years. It's going to be on how do we secure sensor fusion in multi-agent collaborative configurations where we're doing processing at edge devices for collaborative missions. I think it's no surprise to really anybody here or on the call that autonomy is a mainstream facet of our lives now and of the future of technology. From many applications like delivery of medical supplies to remote area, to intelligence operations, to precision agriculture and medicine, and to the transportation industry where we can today, in certain cities, call fully autonomous vehicles, autonomy is becoming a very mainstream part of our day-to-day. Driving this advancement in autonomy, in order to achieve the high expectations that we have for our autonomous systems to safely navigate dense urban environments under challenging adverse situations while transporting precious cargo and humans safely from point A to point B is sensing and perception. Sensing, which takes analog inputs from sensors such as the camera, LiDAR, radar for perception-oriented inputs, and inertial measurements from IMUs, as well as navigation-oriented data from GPS, really provide the gateway from the environmental world into the digital world. Perception algorithms are tasked with taking that analog sensor data, or that digital sensor data, and building up situational awareness, building up an understanding of what's actually happening in the scene, so that downstream algorithms such as path planning and control, which are tasked with planning safe routes through the environment and actually controlling these vehicles to get from that point A to point B, which are very safety critical tasks. Sensing and perception is really this fundamental input into these safety critical modules. And it's what I focused a significant amount of my research on the past 5 years. Since these systems are very safety critical, as you would imagine, a lot of emphasis has been put on ensuring that they are safe. And this has taken the form of millions of testing miles being conducted, in particular in autonomous vehicle applications, in both simulated environments as well as in real world controlled scenarios, and the development of safety aware algorithms such as control barrier functions and formal methods. But extensive safety evaluations under assumptions of benign data don't handle questions of security when there are adversaries in the loop. And as adversaries have become more ambitious, attacking over physical, cyber channels, we need methods of modeling these adversaries and understanding the ability of them to impact our systems. And the safety evaluations that we've relied on for years really don't meet the bill on this. This is important in the face of significant proliferation of a wide variety of attack vectors, including the development of physical spoofing attacks. We partnered with the University of Michigan under this Athena program to design LiDAR spoofing subsystems that were capable of injecting adversarial points into victim vehicles. And precise control of the timing of these components allowed us to place these spoof points in total control in the spherical coordinates of the victims. We've also seen, with the proliferation of wireless connectivity between vehicles and the need to perform over-the-air software updates to update vehicles out in the fleet, the rise of cyber position threats is a significant issue that we need to be considering, especially when these sensors that have high performance often have long and complex supply chains with components sourced from around the world. We've also seen the development with white box optimization techniques of physical adversarial objects that are designed to look almost like benign objects in an environment, but actually have unintended consequences when placed in the scene, such as creating false positive detections or negating the detection, making existing objects invisible in a perception state of in a perception framework. So from this understanding of what the vulnerabilities of the system are, we've asked a couple of questions, such as, are algorithms for sensing and perception, are they vulnerable to certain classes of attacks? And then if so, how can we design them in better ways that enhance security awareness? This has framed my research aims the past 5 years. The first question that we started to look at was whether multi-sensor fusion, or the combination of different modalities of sensors and the algorithms associated with that, were vulnerable. And so we asked questions such as, can an attacker compromise a fusion system by only compromising one of the sensors individually? And can this happen in the real world with only partial knowledge, not full knowledge of the system? We then looked at defense-oriented techniques, such as investigating if collaboration between multiple autonomous agents could secure the sensor fusion pipeline. We looked at how we would frame this in terms of the trustedness of the different agents, and how we would handle this in centralized applications as well as in distributed networks. And finally, a more recent effort was to look at whether we could secure a single platform by extracting additional contextual reasoning from deep neural networks, from the sensor data, using context-aware deep neural networks. To support analysis and research in these areas, we built in this lab a modular autonomy development platform that was mentioned by Vishruth in the introduction. It was built in a response to our observation that a lot of source code and algorithms released in the research community were particularly tied to a data set or a simulator very intimately. So it took a lot of engineering effort to extract out those hard-coded elements. And in response, we built a collection of data source agnostic algorithms across the entire autonomy stack, including incorporating PyTorch models for deep neural networks, which are particularly applicable in the perception domain. And then we combine this with integrations and standardized reference frames, transformations, timing, API calls with state-of-the-art datasets and simulators in a platform that we called AV Stack, that we hope that the research community will adopt and provide us feedback on. With this modular development platform and these research aims, the structure of my research the past 5 years has been in these 3 decomposable blocks. Today, I'm going to be focusing on how we investigated using multiple agents to perform collaborative data fusion. And this is where I start diving into that. We called it trust-based sensor fusion, and I'll be breaking down why we need this trust-based approach and how we're defining trust, how we're estimating trust, and then how we're using it at the back end. Beyond security awareness, there are many environmental conditions that would significantly benefit from collaboration between multiple agents. For example, in autonomous driving, which is one that we look at very closely, we look at safety critical interactions, such as complex intersections, where an autonomous agent is tasked with entering an intersection with cross traffic, obeying traffic signals, obeying the rules of the road, and making sure that they're translating their situational awareness into a safe path that can appropriately navigate these complex situations. But certain things challenge the ability of autonomy to do that. The first of which, most notably, are inter-object occlusions. So in an environment here in the bottom right, I've shown a ground agent with a forward-facing camera. And in front of this ground agent, there are a couple of other vehicles, other objects. These other vehicles are right in front of the ego agent, and so they occlude the field of view of our ego agent, and prevent it from being able to actually fully understand what's going on in the intersection. If we were to place, if this were to happen in a smart city, for example, where we had other cameras and other LiDAR, radar sensors placed on infrastructure, placed on roadside units, these would provide complementary perspectives and enable, through a collaborative fusion approach, enable the vehicle to build that situational awareness that it needs to safely enter that intersection. As we increasingly demand that deep learning is happening for inference on the edge devices, we'll inevitably face situations where we have swap constraints, where the platforms, where either we need to scale down the models to be able to be deployed in real time at the edge, or we need to scale down the size of the data. We need to have lower resolution data in order to meet these, the timing requirements of these autonomous systems. And as a result, agents can significantly benefit from collaborating with other agents in the case that they have to run low swap versions of these algorithms. There are a couple of different philosophies at a high level for how you do multi-agent collaborative sensor fusion. The first of which is a centralized approach, where all agents are connected in a known network topology, and their data at some level is shared with a centralized server that collates and fuses all of the data, time synchronizes it. And the way this would happen is that each of the individual agents is going to be running their own perception and tracking pipelines, and they'll be sending detections or tracks to the central aggregator. This approach is optimal from a data fusion perspective because if you're sending the raw detection information, then the central server can, that's like the maximum available uncorrelated data that it can process. But this is particularly challenging in wide areas where you don't have consistent communication. You may have latency, you may have dropouts. On the other side of the coin are distributed, or also known as decentralized architectures, where agents are connected to each other opportunistically in an ad hoc network where the structure is not necessarily known in advance. In this case, agents will share data amongst neighboring agents whenever they come into or out of communication range. But in this case, there may be some issues that you have to consider, such as what is technically known as rumor propagation, where you have, let's say you had 3 agents, and agent 2 had sent its own data to agent 3, and then agent 1 is receiving data from both agent 2 and 3. So then it's almost in a way double counting the information from agent 2. But it doesn't know that because the topology of the network is unknown. So you have to specifically design the data fusion algorithms to handle those cases. Multi-agent collaborative sensor fusion is great, and when done in benign circumstances can really enhance building up situational awareness that is reliable and trusted and redundant. But unfortunately, it does lead to the problem of what if an agent is potentially compromised? Any of these agents in the network could be compromised, and if they are, particularly if we're in an environment, say where we're collaborating with agents of different nationalities, of different vendors, sensors with different length supply chains, but we need to do so in order to build up our situational awareness in like an intelligence operation. We want to use all the maximal information that we can, but we don't necessarily know if any of these agents are lying to us or are maliciously compromised. So this concept has framed our research in multi-agent collaborative fusion. looking at how can we first detect that there's asynchronicities or anomalies that are in the network. And beyond just detecting that there's an anomaly, then we move into how do we identify which agent and which set of information is the malicious set, and then are we able to fuse the data despite there being the presence of adversaries? This is challenging because in a threat model where any individual agent can introduce, if they're performing object detection, trying to track objects on the ground or build up an understanding of mapping, any individual agent that's compromised can introduce false positives and false negatives into the picture. And under a situation where you're sharing all this data and one agent maybe reports the presence of one object, but the other two agents disagree and don't report that object exists. Meanwhile, some other objects are observed by all of the agents. There's a significant amount of ambiguities about who's right here. Who do we trust? Who do we believe? Do we take everybody's data? And this can cause problems of the naive approach is just to take all of the data in and fuse it and then send it on its way. But this can lead to issues where a single adversary can just simply flood the network with false positive detections. And what you'll see here, pause the video here. You'll see here in the top right, we have a ground agent that is uncompromised, and it has a particular view of the world. In the bottom right, you have agent 3, which is an infrastructure agent, and it has been compromised. So it's introducing false positives into the network. This is a centralized architecture, and CC denotes command center here, which is a centralized fusion. When that information gets fed back to each of the agents, those false positives will show up in front of the ego's view. And if we don't have any way of identifying that these were actually disagreements, then it can lead to safety critical incidents, such as activation of emergency braking or evasive maneuvers. We did a survey of the existing methods to handle consensus and multiple target tracking with some security awareness, but we found that many of them fell short in different ways. We looked at the track scoring algorithm, which is a method in multiple target tracking, which intends to build up a hypothesis test, likelihood ratio, between the hypothesis that any individual object that's being tracked by multiple agents simultaneously is a true object or whether it is a false alarm. And this works really well when you have understood benign models of how the sensors perform, what their natural false positive rates are, what their natural false negative rates are. But under cases where you have adversaries that aren't obeying these natural sensor error models, we showed that you can provably compromise the track scoring approach for integrity, even in the case where the number of benign agents outnumber the number of adversaries. So even if the adversaries are in the minority, they can easily compromise the track score using just, and we showed that by illustrating conditions under which the gains for the true target hypothesis from the adversaries outweigh the loss from the benign agents. We looked at Byzantine models for consensus, which are popular in multi-agent computing and distributed computing in particular, but found that these broke down for several other reasons. One of which is that many of them fall into the category of autonomy has just special considerations that distributed computation does not have, such as the presence of field of view models and the influence of inter-object occlusions. A sensor out in, say, the desert or in a wide open environment may have a predictable circular or spherical field of view. But once you put this in a more dense urban environment, you're going to have occlusions that limit the field of view. And we can't just assume a simplistic circular model. We need something to estimate field of view online. These methods also often assume that perception is error-free, meaning they don't handle cases of natural false positives and natural false negatives that are going to occur out in the real world due to the stochasticity of sensing and the environment in general. So from some of these shortcomings, we wanted to take a new approach, which is to integrate a notion of trustedness into the sensor fusion problem. We did so by, in addition to collaboratively tracking the locations and sizes of objects in a given area, we're also going to be tracking the trust of each of the agents that are participating in the sensor fusion problem. We're representing trust here as a probability density function on the domain of 0 to 1. We're using a parametric beta distribution because of its natural domain on 0 to 1, and it has good properties that make it computationally efficient. And we'll be introducing 2 additional variables into this data fusion problem. The first is the agent trust, which is generally the belief that each of the agents is contributing data that is valid, consistent with physics, and consistent with the majority or a trusted consensus of other agents. And then there's the track trust. And these tracks are the objects that we are monitoring on the ground. And the track trust that we're going to be maintaining is the belief that both an object exists and that the state that we're estimating is accurate. We call these tracks because the tracks are kind of hypotheses on we think that there is an object there with some probability. And the states that we're estimating here are going to be your kinematic states, so the position of an object, its velocity, and its bounding box size. The beta distributions, to give you a sense of how they are visualized, are shown in the bottom here. Like I mentioned, they're on the domain of 0 to 1. Introducing a little bit of math and notation here, just to show you how we're doing this formally. We took the classical state estimation problem, which is the goal of estimating the distribution over all of the object states in an environment. And these are the positions, the velocities, the accelerations, and the existence, and the bounding box size, and the existence of objects. The classical state estimation problem is to estimate the distribution over those states given any measurements from agents, measurements being camera, LiDAR, radar data that are then translated into detection semantic data, as well as it's a function of characteristics such as the sensor field of view and the agent position and orientation at that particular time. We took this classical state estimation problem and augmented it with 2 additional variables. So now, in addition to object states, we're also estimating track trust and agent trust. And with this, we can use conditional probability to decompose it into 2 subproblems that make it an iterative process. That first subproblem is to perform trust estimation, where we're estimating the PDFs of the trust variables given the measurements. And then the second is going to be trust-informed state estimation, where we're estimating the object states given our trust that we just estimated. How this fits into the entire pipeline is what I'm going to show here. So in a centralized application where you have multiple agents that are doing their own perception, so they're taking LiDAR camera data, they're passing it through deep neural networks, they're getting object detections, which are these bounding boxes I've shown in green. Each agent is going to be doing that locally in this case. They can also run tracking locally, where they recursively filter these detections to build up consistent knowledge of IDs on these objects, and also to filter out natural false positives and negatives. And in the centralized case, they're going to be sending all of this information to an aggregator that's tasked with time synchronizing, assigning all of the different objects between the 2 sensors, and then fusing them together. To complement this with the trust, we've built out an additional trust awareness node where the tracks are and the aggregator states are fed to this trust awareness block that performs a 3-step process that I'll spend the next section talking about, where we're actually like taking these and estimating the distribution over trustedness for each of the agents and each of the tracks. Then that trust is fed back to the aggregator, which can then use it to inform the fusion problem. In a decentralized approach, it works similarly, except in this case, instead of there being a centralized node where all the trust estimation is run, all of this is happening on the edge device individually. We typically see decentralized applications in UAVs due to the larger areas that they're operating over. But there are also other applications where this would apply. In this decentralized case, an agent locally will be running perception tracking, and then it's also going to be running the trust locally. So in this next section, I'll be going through that first subproblem that I broke out, which is the trust state estimation subproblem. We're framing this as a hidden Markov model where we have trust as a hidden variable, and we need to use our available measurements from the sensor data to estimate it. We're taking a recursive framework to solve this hidden Markov model, to solve the hidden Markov problem. And we're doing so in 3 steps. First is propagation, where we take the most recent estimate of our trust and we bring it forward, we propagate it to the current time with any dynamics or evolution models. The second is the generation of trust measurements, where we're taking our available sensor data, which is not on the trust domain, which is 0 to 1, and we are running some logic to back calculate what a trust measurement would be. And then finally, we're taking those measurements and we're updating our PDFs. These 3 steps happen sequentially, and then the whole process is repeated recursively over time. We're taking a Bayesian approach here, where we specify prior information if it's available to us. And this is a particularly attractive approach to take, because if we have that prior information available, such as knowledge of a very trusted agent in the environment a priori, that can help us stay resilient even in the case where we are outnumbered by adversaries. It also allows us to leverage conjugacy conditions that make these updates very, very efficient and able to be executed in real time online. I'll walk through each of these somewhat quickly. There's a little bit of math that I probably won't dive too far into. But the first step in solving this hidden Markov problem is propagation. This is where we bring that last trust estimate to the current time. And we wanted to implement propagation models that follow the intuition that without any new information on the scene, we would generally expect that trust should become less certain over time if we don't get any new knowledge. And we determined there were at least three ways of representing this. The first is propagation of the expectation of this distribution. The second is of the variance. And a third is interpolating the last estimate with the initial prior that we set. Visually, I'll show these at the right here, where propagation of the mean takes the blue, which is our most recent state estimate, and shifts it back towards some reference, which could be towards the center, to reflect that we are less certain about our trust estimate. Variance propagation, which is slightly orthogonal to this, is to keep the expected value constant, but effectively increase the uncertainty on our distribution to reflect the statement. And then the last is taking some reference distribution. That's the one we've shown in the dashed red, and then interpolating the most recent one with that one. Then arguably the most important step is to generate trust measurements. This is where we take any available sensor data and we have to map it onto the 0 to 1 domain to represent how trusted was the most recent set of data that we got. We wanted to represent this trust measurement. We call them pseudo measurements because there's no trust sensor that you can throw in a platform that's going to tell you exactly the trustedness. So we have to derive our own measurements, which is why we call them pseudo measurements. We represented this as a tuple of a value and a confidence, much like a GPS sensor would give you a position estimate and perhaps an uncertainty on that position measurement. The basic backbone of how we're doing this is evaluating some notion of predicting what an agent should observe and then evaluating what it actually observed and analyzing any discrepancies therein. In the centralized case, we're comparing each agent to the central aggregator. And in the distributed case, we compare each agent with its nearby agents, with anyone that's communicating with it. This is where that field of view model comes into play, like I mentioned earlier. Out in the real world, sensors are not going to have perfect fields of view. They're going to have regions of space that they can't see because of occlusions due to walls or other objects or buildings. And so we have to build up a field of view model online for the purpose of, we don't want to penalize an agent for not observing some object that it was never able to see because that object was, for example, behind a wall. This is the overall block diagram of how we're building these pseudo measurements in a centralized case. And I'll just say at a pretty high level to walk through what's going on here. We're starting off by taking any individual agent's tracks that are maintained locally, taking the tracks that are maintained at the aggregator and doing an assignment between them. So matching the hypothesis that this track from the agent is representing the same object as this track from the aggregator, so that we can compare, did we have the same or did we have different visibility? Any assignments? So this is where we did find a match between agent K is tracking the red car and the aggregator is also tracking the red car, and these are the same red cars. Anytime we have that assignment, we're going to run this logic at the top here. The blue parallelograms are the pseudo measurements that we derive for the agents. And you'll see two components of this. The V is the value and the C is the confidence. The green is going to be the pseudo measurement that we derive for each of the tracks. And once again, the V is the value and C is the confidence. And you'll see these are intimately related in a recursive format to the actual distributions that we have over the trustedness. And it would take me a little while to go through actually the logic behind this. But the basic idea is that if an agent sees something that the aggregator also saw, and that thing that they saw is trusted, then we should increase the trustedness of the agent more. If they saw the same thing, but that thing is distrusted or it's not believed to exist, then we should decrease the trust of the agent. A similar thing happens when we don't have assignments. So if we have a case where the aggregator sees something that the agent doesn't see, or if the agent sees something that the aggregator doesn't see, we run a similar logic, but in this case, it's actually basically the inverse of the pseudo measurements. I alluded to this, but being able to accurately predict what an agent should see depends heavily on the field of view of each of the sensors. And we looked at a couple of different ways to model the field of view. In this case, I'm showing just visually why this is important. We have a ground vehicle here who has a camera and a LiDAR, and it's detecting two objects in its front view. But these two objects, because they're right in front of the ego agent, are including a significant fraction of the field of view, such that when you look in the LiDAR point cloud, there are regions of space behind these objects that are invisible, or even if an object were there, we would not be able to see it. We looked at a couple different methods for being able to estimate fields of view from sensor data online. We looked at ray tracing techniques, which are popular in the computer graphics community. And we also built out deep neural networks to perform segmentation, taking the LiDAR data as input and predicting field of view as output. And we found that this approach was significantly more robust to noise or to even adversarial actors than the ray tracing methods. Finally, with this collection of pseudo measurements in hand, we can actually update the probability density functions of the trust estimates. And I mentioned the Bayesian approach that we took earlier. This allows us to do these updates really quickly and easily. If we specify that the prior on these distributions is a beta and the likelihood function is a Bernoulli by conjugacy, it will yield a beta posterior. And with two parameters from the beta, the updates become very, very simple and efficient. If a pseudo measurement is a tuple of value and confidence here, and the general form of a Bayesian update for two parameter is that the parameters for the current time are the parameters from the previous time plus some delta. The delta can be shown to be just simply the summation of the product of the confidence and the values for the alpha parameter, and the confidence and the inverse of the value, or 1 minus the value for the beta parameter of the beta distribution. And this is the statistically correct derivation of how to do the update. But we wanted to take it one step further and relax a little bit of the statistical correctness to achieve something that was a little bit more intuitive. In this case, we wanted to match the intuition, which applies both in autonomy and also other networks, such as even in social networks, that trust should be built on large amounts of consistent data, but trust can be lost on even small amounts of inconsistent data. To enforce this intuitive property, we introduced two new parameters, a negativity bias and a negativity threshold. And where we had those updates before with the deltas now becoming, the delta alpha stays the same as just the product of the confidence and the value, but the delta beta, we've introduced this additional weighting parameter, which is a switch statement of here when the value is below the threshold, it's going to be this negativity bias B, and if it is above, it's just going to be 1. And this allows us to give disproportional weight to any disagreeing or negative information so that the system can react faster to the presence of adversaries. That concludes the first section on how we're estimating trust. This next section is fairly short, and it's on how we're using trust to inform the data fusion process. We have 2 different trust estimates. We have the agent trust and we have the track trust. And we have 2 different architectures, centralized and distributed or decentralized. And these require slightly different ways of utilizing trust each. I'm going to be focusing on how we use agent trust. How we use track trust is a little bit, is part of my subject for future research. We believe trust on the tracks can be very useful in directing mission planning, resource allocation operations, where you're actually commanding, where you're doing trust-informed planning, where you're commanding these platforms to go investigate certain regions. The track trust can be very helpful for following up on distrusted objects. And then agent trust is used to weight the influence that each agent has on this global operating picture. I'll dive a little bit into how we're doing this for the distributed case because I think it's particularly interesting. In a distributed context, classically, the way to fuse information in the presence of unknown network topologies where you may have correlations between the information that's being shared around to different nodes is to run a distributed data fusion algorithm. The most popular one is called covariance intersection. And the general process is that each individual agent is running its own data fusion. When it receives information from another agent, it'll run this covariance intersection algorithm. Then it waits to receive from some other agent, and it will run it again. So it's a pairwise cascaded fusion approach. And the approach for doing so mathematically is written here. And it's really not that intimidating. It's just each agent is providing mean and covariance estimates, so like an estimate of the state and the uncertainty. And then you define an optimization criterion. So you say, I want to, the basic goal is to come up with some weighting parameter W that says I want to take this proportion of information from agent 1 and this proportion of information from agent 2. And that proportion factor W is what you have to figure out, like how much do you weight them. The naive approach would just be to take half of each, but that doesn't account for the potential of correlations. So in an optimization loop, you keep iteratively doing this process in order to find the optimal omega parameter that minimizes some criterion. That's the classical way to do distributed data fusion. And we've proposed an augmented approach to do so with trust as the weighting parameter instead. So this covariance intersection algorithm is modified slightly so that now instead of doing pairwise, we're just doing all of the available state estimates jointly at one time. And instead of running an optimization to get the weighting parameter, we're setting the expected value of the trust for each of the agents as the weighting parameter. The fusion still happens in the same, what's known as information form of the Kalman filter, where you're just multiplying each of the uncertainties and the mean values by this weighting parameter omega to get the fused solution. We took it one step further, and we also built out a confidence measure on this by looking at the variance on all of the trust distributions, tau here being the trust distributions for each of the agents. If we have a collection of agents with very uncertain, very unknown trust, then we want to reflect the fact that this fused solution may be very uncertain as well. And that's where this last fusion confidence comes from. And now on to the last part, which is where I'll go through a couple of case studies and look how we evaluated this qualitatively and quantitatively. To evaluate this in multi-agent configurations requires multi-agent data. We found that not very many sources of multi-agent data existed, so we decided to use our tool AVStack to build our own multi-agent data sets. We did so first in a ground vehicle application where we had multiple ground agents traversing an environment with camera and LiDAR sensors. We also placed a collection of infrastructure agents that were doing camera and LiDAR sensing. We placed them on traffic lights, on roadside units, and on buildings. We did the same in aerial applications where we put sensors up in the sky and looked at downward-facing data, camera, LiDAR, radar. And in order to make this a data set that we could use for testing, we built a ground truth labeling tool on top of the Unreal Engine simulator, Carla. We stood up autonomy stacks so that we could evaluate these to see if they would be executable in real time. So we used the robot operating system along with algorithms for perception, tracking, and data fusion to set up playback situations in real time. What you'll see here are two perspectives on a scene where each of the different agents has a LiDAR sensor, and each agent's LiDAR sensor is coded with a particular color, the yellow being the ground agent and the other colors being the infrastructure agents. You can see the field of view models that we're simultaneously estimating online are the solid color lines that bound all of the LiDAR points. And you'll see a collection of green boxes. The green boxes are the result of fusion from this centralized server, where all of these individual agents are sharing their detections. The central server is performing the fusion and sending back the green boxes to be visualized. Yeah, you can just kind of watch it for a second. Cool. I want to briefly discuss what metrics we're using to evaluate how well this is performing. And I'll start off by looking at some classical detection and tracking metrics, where we're taking a set of truths or we have an oracle that knows exactly where things are, and then we're comparing the tracks that we built by this collaborative sensor fusion process. The metrics that we use to evaluate this, we used classical assignment-based metrics. So these is the precision, the recall, the F1 score that you may be familiar with from object detection problems. And we also looked at a couple of tracking-based metrics, in particular the optimal subpattern assignment that uses a weighting of multiple costs. So it looks at the entire track state estimate. It compares how well are we estimating all these states compared to the truth. And then there's also a cardinality penalty that penalizes for introducing too many false tracks, too many or missing too many tracks. And there's also an optional labeling penalty for classification problems where if we misclassify a car as a pedestrian, it includes that as a penalty. Then we also built out a couple of novel metrics to capture how well the trust estimation part of this subproblem is performing. We looked at, in order to quantify this, since the trust is maintained as a probability density function, we wanted to look at the distance between the ground truth PDF of the trust of these objects and the actual estimated PDF. And the way we did that is by measuring the distance between the CDFs or the integral over those PDFs. I won't go through this in too much detail, but the metric actually really simplifies, is the moral of the story here. To just, we can just represent the distance between these two as simply the expected value of the PDF. So all we have to do is try and maximize that mean of each of the trusts towards either 1 in the case of where it's very trusted, or 0 in the case that it's untrusted or distrusted. And that's the metric that we're going after. So in this case, we took 3 infrastructure agents and one ground vehicle. We introduced an adversary onto the ground vehicle, agent 0, and introduced 4 false positives into agent 0's detections. In this case, we're trying to use trust to quickly identify that agent 0 is the compromised one. And this is what you might see as a graphical user interface of what's happening here. On the top left, you have the view from one of the infrastructure agents. On the bottom left, you have a view from the ego agent. It's maintaining a bunch of different tracks, and any track that's in red with the red marking is a false track that has been adversarially injected into agent 0. After running this trust estimation process for some period of time, we can quickly see that the mean value of the trust distribution in the top right for the agents has identified that agent 0 is not trustworthy. It's also identified the 4 tracks that are false positives by indicating that they have low trust as well. Taking a look at the metrics for this particular case, where we have our ground and our infrastructure agents, we looked at the precision, which is the ability of a detector to produce relevant positive examples. And we'll see that in the attacked case, which is the right column, compared to the benign situation, we have a significant drop in the precision for agent 0. And the aggregator without security, so this is when we're not running any trust awareness, also drops the precision. But when we introduce that security awareness, we can return the precision up to its normal operating value. For the optimal subpattern assignment metric, we also see a similar behavior where there's when the attack starts, which is at t equals 2, there's a dramatic rise in the OSPA for both agent 0 and the aggregator. But when we introduce security awareness, this metric goes back down towards 0, which is the goal. Looking at the trust metrics, we can see in the benign case a high level of accuracy of the trust state estimates. In the attacked case at t equals 2, we have that momentary drop when agent 0 is started to become malicious. But then we get a recovery of the trust. It stabilizes very quickly over time as we use this information to figure out that agent 0 is actually distrusted. And then finally, we ran a large number of parametric evaluations where we looked at how does this trust perform as a function of different variables, such as the number of agents in an environment, the density of agents, the size of their fields of view, and the number of adversarial agents. I don't have nearly enough time to go through all of these, but just one particular example is that as you increase the number of active agents in an environment, your ability to accurately estimate the trust increases with time, increases with the number of an increase in the number of active agents. And this makes sense because you're getting increased and enhanced redundancy of the fields of view. So you're getting more confirmation that you either are or are not observing something. And with this, I'll wrap up here and say there are lots of avenues for future research. We're really just scratching the surface on this, and I'd be happy to take any questions. Yeah.
About the anniversary model detector, is it designed so that for the false positives, they didn't choose for whichever regions they put the false positive, or they optimize to see like what sensors might also see the regions to make it easier or harder for me to do the attack. That's the anniversary model.
Yeah. So the question is about the threat model, the adversary model, and what information the adversary has available to them, and whether they're selecting their attacks in any sort of optimal manner. And that is a really good question, because there are certain cases in which an adversary can launch an attack that is undetectable. For example, if you don't have full redundancy of your field of view, and there's a particular part of your field of view that's not observed by any other agents, an attacker could put something there, and then there's no chance of that ever being validated or invalidated. And yeah, that is definitely a significant shortcoming of any approach, really. If you don't have any level of redundancy, there's almost nothing you can do. So to obtain that information, though, would require either an understanding of where other agents are, other agents that are not compromised, or an ability to directly observe other agents in the environment. And that's just a large assumption that that would be pretty strong. So we just kind of state that the adversary is on a limited number of agents, and there's minimal communication between, there's minimal ability for an adversary to collude or coordinate amongst other agents. But it's definitely an issue that is hard to solve.
Hey, Spencer. Question online. This is Christopher Hayes with the Air Force Research Lab. First off, great talk.
Any
Yeah,
high school questions? High school student questions?
What would be the next step in your research?
I think one really interesting avenue is how do we use this trust to inform mission planning and resource allocation? For example, if we in these situations, we just pre-programmed the agents to go on like a predetermined course, but could you program them to react to changes in trustedness of other agents? Like if you saw, or could you program them to mitigate field of view issues? Such as if you had the case where you had a track that was in a region that was only being observed by one agent. And so therefore you knew that like you couldn't build up trustedness on it. Could you then command another agent to go and view it so that you have this redundancy? I think that would be a really interesting research avenue of using this trust to inform mission planning so that you can mitigate all of these corner cases where adversaries could exist. And can you detect things that weren't possible before?
One more question? All right, someone wrote in online. Spencer, can you comment on the tightness and or conservativeness of the truth-informed information fusion scheme? Seems like assigning the weights based on the trust metric would introduce over conservativeness.
So yeah, I think you're talking about the covariance intersection algorithm. We did not really evaluate any formal guarantees of that method. There certainly could be conservativeness introduced into that. Some conservativeness, especially in a decentralized approach, is by design, because if you're not conservative, even if you take the adversary out of the equation, if you're not conservative, you could run into situations where you become overconfident by accidentally double counting information that has been provided to you by multiple sources simultaneously. So we wanted to maintain that level of conservativeness so that we didn't run into those issues. In the centralized context where you're looking at the Kalman gain and you're in that part of the fusion, you're directly applying these weights. There needs to be a normalization to make sure that you're not being too conservative. So that is a good technical point that you bring up there. Cool, thanks.
Do any